analysis, significance testing, it is time for us to move on to Bayesian statistics, specifically Bayes' theorem. Now, Bayes' theorem falls into the arena of conditional probability, and as such is computationally simple but conceptually complex. So let's jump right into our example. So let's say we are looking at testing. And one of the things we'll need to know if we're in a testing scenario, let's say we're interested in finding out of those who failed, what percentage knew the material. So let's first begin by saying that n is equal to 1,000, or rather 1,000 people took this test. And that of that 1,000, 70% knew the material and 30% didn't. That gives us 700 who knew, 300 who didn't know. Next, we need to know the percentage of those who know who failed. So let's say that 5% of those who knew failed. Next, we need to know what percentage of people who didn't know failed. Let's say that 80% of those who didn't know failed. From here, we can figure out what percentage of people failed or didn't fail, and then of the percent that knew, how many, or rather out of the percent that failed, how many of those people knew the information. The simplest way to look at this is just in a box. Let's make the box out of black. Make this nice and simple before getting into Bayesian's formula, or Bayes' formula. So in this box, we're going to have two types of people. We're going to have those who passed and those who failed. We're also going to have those who didn't know and those who knew. So we know that 5% of those who knew failed. So they know and they failed 5%. And we know that 80% of those who didn't know failed. Now, we can complete this box because these rows sum to 100, or to 100%. So we know that for 5% to have failed, 95% of those who know needed to have passed. And that of those who didn't know, since 80% failed, 20% passed. From here, we could run our computation. We could say that since there were 1,000, 700 of whom knew, bring that down, 700 of those knew, 300 didn't, we can go ahead and write in our information. We can say that of the 700 who knew, 95% passed. So if we're looking for those who failed, we just take 700 times 0.05 is equal to, 700 times 0.05 is equal to 35. So you know that 35 of those who knew failed. And again, that means that 700 rather, minus 35 gives us 665. And then if we repeat the same steps down here, we know that of the 300 times 0.8 for the 80% failure rate gives us 240 people. And that over here, this will give us just 60. So this is a breakdown in 2x2 box form of what our Bayesian theorem is going to give us. And if we wanted to get that information that we're going to pull, we would just take this and we say we have 35, our part of those who know, out of a total of 275. Whoops. Yeah, we'll just leave it. Just do it, pretend it's a fraction. We'll divide it that way. But 35 out of the total number of people who failed, so 240 plus 35, so 275, is equal to the percentage of those who failed who knew the material. So 35 divided by 275 is equal to 0.127, or 12.7% of those who failed knew the material. Now, since you're most likely going to have to do something with the Bayesian version of the formula, let's go ahead and begin calculating that. So let's say that we are looking at, again, still the percentage of those who know who failed. And that this is equal to the Bayesian theorem formula, or rather that formula will give us the answer, the same answer that we had up here from our box. We're going to need the, well, let's color code this since we repeat terms. So we're going to have the percent of those who failed, who know. We're going to multiply that by the percentage of those who knew. Not too bad so far. Then we get over here. We repeat these terms down below. So percentage, those who failed, who knew, times the percentage of those who knew. And again, we'll put that multiplication term in there. Then we add to that the next set of terms. Our percentage of those who failed, who didn't know, times the percentage of those who didn't know. So you can see that this is giving us the same idea as what's up here. And if we go ahead and pull this down, we can go ahead and calculate, and you'll see that you have the same answer. So the percent know who failed, done with that one, again, is equal to, and we're just going to pull our numbers down here. So this term is equal to that 5%. Since it's not very convenient to deal with percentages, we're just going to deal with this as a decimal. So 0.05 times, and then what percentage knew? 70% knew, as you see up here. So times 0.70. And all of this is over 0.05 times 0.70 plus our term over here. So the percentage of those who failed who didn't study, that 80%, so our 0.8 multiplied by those who didn't know, so that 0.3, and that is going to give us, we'll use black for all of our computation, is equal to, well, let's see, 0.05 times 0.7 is equal to 0.035 over, well, we know that this is going to be 0.035 already, plus 0.8 times 0.3, so 0.24 plus the 0.035 from the other term gives us 0.275. And if we calculate, if we look at this, we're seeing that in decimal form we have what we had up top. We have up top we have 35 over 275, and here we have 0.035 over 0.275. And if we divide 0.035 by 0.275, we're going to get 0.127, which is exactly the same answer that we had above. So of those who failed, 12.7% knew the material. And so they failed for reasons other than not studying, not knowing the material. What those are not apropos to this example, though I'd like to discuss them as a retired teacher, but we'll leave it there. So this is how we run through Bayesian formula, and I hope that this box up here helps you see where we're getting this from. That each of these terms comes from this box. That yes, we may see them in a written form, and we could skip the box, but that the box is useful in that it simplifies our conceptual finagling and trying to fit things into the right spot. And I found that that's very helpful, especially in areas where you're not using a formula very often, or it's a new formula or a complex formula. I would recommend filling out the box and only going down to the formula if you need the formula. However, the formula is nice to be able to use. It does add to that area of just making things very simple in showing you, well, I have this term and 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 this term. And if I just plug in all those numbers, then I can just follow my order of operations and boom, I have my answer, as opposed to having to keep that in your head like up at the box. But I'll leave that up to you. The only other thing I'm going to bring in is how we use this for dealing with issues in null hypothesis significance testing. Or rather, the formula you would use if you were to do that. So let's say we're looking at the percentage. No. Actually, let's stop right there. The purpose of this video was to show you how you calculate this formula, not how you use it to deal with the issues of null hypothesis significance testing. So let's stop there. And if you are in desperate need of how you use this in null hypothesis significance testing, you can let me know and we'll deal with it then. So until next time, cheers.